So today we're going to be looking at uncertainty in AI. So this is the first AI lecture in Texiland, but hopefully everything's right. If there's any questions throughout, just let me know. Okay, so when we talk about uncertainty in AI, it refers to situations where the outcome of a state or system is not fully known. That seems like a lot of waffle, but all it is when we can't guarantee that something's going to have some sort of specific output or some specific outcome. Now, there's different things that cause this unpredictability or this uncertainty, and the things we're going to explore are data uncertainty, model uncertainty, and environmental uncertainty. So we'll start with data uncertainty. This is when the actual data that we've got, like the training data, is noisy or it's incomplete. So this might be due to poor methods when like collecting that data, or corruption of that data when we're trying to store it in one format or another. Then we also have model uncertainty, and this is because of limited or incorrect model assumptions. So if we have a model that's maybe overfitting or underfitting, that could cause some sort of uncertainty. If our model parameters are not optimal, then that could cause uncertainty, because or if we're using like the wrong model for a certain problem, like a classification problem or a regression problem, and we're using the wrong model, that can also cause uncertainty in those domains. And then we also have environmental uncertainty. Now this one's more unpredictable because it depends on things like the weather, things that are out of humans' control, and that affects data and creates these unpredictable patterns in data. But we can also split uncertainty into two different types of uncertainty. So we can model predictive uncertainty as y, which is our target sort of output, minus f of w hat x. So y is essentially our true values, our true outputs, and this f of w hat of x is feeding our inputs into a model with our model parameters. So w hat is the parameters of our model, which we trained on a training set that we get. And all this is it's the difference between the true distribution of data and the distribution that our model tells us our data is in. So predictive uncertainty is made up of two parts: aleatoric uncertainty and epistemic uncertainty. This formula might seem a bit confusing right now, but we'll explain the different components of it and why that sort of makes up this formula. Some of the predictive uncertainty can be reduced, whereas some of it can't. Aleatoric can't be reduced, whereas epistemic can be reduced, and we'll see why that's the case. So starting with aleatoric uncertainty, we can't reduce this, and this is because it arises due to intrinsic randomness in the data or process. So this was me talking about things like environmental factors that affect data or that might corrupt data. For example, sensor noise in autonomous vehicles is something we might not be able to cut out. If we have some sort of interference with things like radio signals or sound, we can't necessarily cut that out with a guarantee that it's been cut out. And so this leads to aleatoric uncertainty. We can't reduce it, and it's not because of poor model parameters. It's because of intrinsic randomness in the actual data that we're collecting and that we're using to train our models. And then we have epistemic uncertainty. So this can be reduced, and this is because this arises due to a lack of knowledge and is reducible with more data or improved models. So essentially, if we have a model that might have suboptimal parameters, that's an example of epistemic uncertainty, because we can find more optimal model parameters that model our distribution more accurately. It's just that we've not found those parameters yet, but it's something that can be reduced as we as we are exposed to more data and we train the model with more data. So when, for example, ChatGPT hallucinates, it could be an example of epistemic uncertainty if it just hasn't been trained on enough data in the topic that you're like asking it about. That uncertainty is reducible if we just fed it more sort of like news articles or any sort of training data that can help it improve its knowledge in that area and give better outputs. So I've got a diagram here. One of these colors represents epistemic uncertainty and one of these colors represent aleatoric uncertainty. Which one do we think is which? So remember, one can be reduced with like improved model parameters, and the other can't. Okay, so blue is epistemic. Yeah, good. And so red is aleatoric. Why are we saying blue is epistemic? Does anyone want to explain? You can also raise your hand if you want to talk, or you can just type it in the chat. No data points. Okay, good. Yeah, so because we don't have any data points, that's epistemic uncertainty, because with more data points we can train the model well. And then why is red aleatoric? 1 second, that's my doorbell. I'm back. Sorry guys, my doorbell rang. That was some aleatoric uncertainty. Right, blue is epistemic because it's no data points. And the reason why red is aleatoric is, as you said, cool, randomness. Perfect. Yeah, so because there's randomness in the data, it's not something we can quantify with a simple sort of like distribution, a simple model. And so that's why it's intrinsic randomness in the actual data. What's X and Y in the graph? So X is just the input and Y is the output, as Manu said, So it could be anything, but X just represents some sort of input into the model, and Y is what that model then says the output is. Or like the true value of that value in the distribution of the data. Cool. Okay, so moving on to different frameworks. So first of all, when we talk about inference, we're talking about trying to find the underlying, sort of like the underlying distribution of some data. And so there's two main approaches we can take. We can either take a Bayesian approach, or we can take a frequentist approach. Now, each framework relies on different philosophical perspectives on probability and modeling. And so there's different things that lead to different types of like different approaches to how we can infer the underlying distribution. So starting with a Bayesian framework, it's named after Bayes' theorem. So uncertainty is represented as a probability distribution, which incorporates some prior knowledge. So if we remember Bayes' theorem, we will have a session going into more detail on this, but it's P, for example, X given Y. And we have some prior knowledge which informs our overall probability. And so in a Bayesian framework, this distribution that we believe the data to be modeled with is updated as we see more and more data. It informs our like how we can update our model and make it more optimal. So parameters in a Bayesian framework are treated as random variables, and data is non-random. So we know the data's there, and we know the data is sort of fixed. But random variables, the reason why the parameters are random variables is because we believe that it's something that we don't know, and it's something that we can't really predict, and there's no sort of set parameter that is perfect for everything. We also interpret probability as a degree of belief. So it's more of a psychological thing. It's more of a we think this will happen. If we think something will happen with complete certainty, it'll be a 1, and if we think it will never happen, it'll be a 0. But any sort of numbers in between that is just a degree of belief, taking into account prior knowledge and things we already know. And with a Bayesian approach to inference, we can quantify and we can update epistemic uncertainty. So remember, this was the uncertainty we said we can reduce. As a Bayesian, like using a Bayesian framework, we can reduce this epistemic uncertainty by trying to find better model parameters which better suit the data we're seeing. Then we also have the frequentist approach, or the frequentist framework, and here uncertainty is based on the long run frequencies of outcomes. The name sort of gives it away, but data is treated as a random draw from some unknown distribution, and the model parameters are non-random. So data is random, which means that we don't know what we're going to see when we like pick something from a bag. Imagine we had the bag of marbles. We don't know anything about the distribution or anything about the marbles that are in that bag, but the model parameters are non-random. So even though we don't know what the sort of distribution of marbles is in the bag, we know that there is some distribution. And so if we can find a way to model that and find the optimal set of model parameters, we can say with some sort of confidence that the next marble will be red or the next marble will be blue. So frequentists essentially believe that there are some optimal model parameters, we just don't know them. And the only way we can know them is if we know every single piece of data, which is impossible, because the probability is just based on the long run frequency of events. So we rely on observed data. So any sort of data we see through loads of test trials and through loads of experiments, that's how we can estimate these model parameters that are non-random, that are fixed. And so we can get closer and closer to the optimal model parameters, but we cannot say for sure that we're at the optimal set of model parameters. It's like there's some sort of truth, but we just don't know if we're at that truth or not. It just exists. Uncertainty is quite similar to probability in a frequentist framework. It's also interpreted or based on the long run frequencies of outcomes. And we use confidence levels, and we use things like test set bounds and train set bounds, which we'll also have a session on, which tell us how likely something is to occur and with how much confidence, instead of just incorporating prior belief. So frequentist approaches are much more mathematical and much more sort of strict and rigid, whereas Bayesian approaches are more, oh, we have some data based on this, do you think this is going to happen, do we think it's not going to happen? So moving on. Oh, okay. Well, that's the end. That's everything in terms of uncertainty. I think a lot of the things that this applies to is like going to be incorporated into future sessions, like how we can find like optimal model parameters, things like that. But are there any questions about any of the theory that I've covered today, or like anything to do with uncertainty in general? I saw a few questions in chat, but I think they've been answered. Oh yeah, I can talk about the formula quickly. So we have this formula for predictive uncertainty. Now, this part here is aleatoric uncertainty, and this part here is epistemic uncertainty. So our aleatoric uncertainty is just the outputs we have, take away g w star of x. So what this is is so w star is our optimal model parameters. So this is the best possible model we can have. Given like whatever model we're using, these are the best possible parameters we can have for that model to represent the data. And so this GW star X is just the best possible representation of the inputs we can sort of predict with our current model. And so why take away this best possible model is aleatoric uncertainty. We can't reduce that by improving the model parameters because we're at the best possible parameters that we have. And then epistemic uncertainty. So GW star X, we've said this is just the optimal model predictions. And then F of W hat X, this is the model we currently have. So the difference between the optimal model and the model we currently have is something we can reduce, right? Because we can go from our W hat parameters to W star. We can change our model parameters. And so this difference is something we can reduce. This difference is something we can't reduce. And to get the overall formula for predictive uncertainty, this minus GW star plus GW star, these two terms just essentially cancel out. And it just becomes Y take away our model's predictions. So that's how that formula is sort of derived. Does that make sense? So Y is in a perfect world, so it's not realistic. Y is in a perfect world, so it's not realistic. GW star is the best realistic parameters, so Y minus GW star equals the uncertainty we can't control. Yeah, that's perfect. Let me just make a... Okay, basically, yeah, so if we have a let's say green is our data. So we might have a model which models this data with this yellow line here. So this is our model. Let's call this f of w hat x, and this is our x-axis, this is our y-axis. Right, so we might model it with this yellow line. A better way to model this data would be this pink line, right? Let's say this is the optimal model parameters that minimizes like this distance here, so L1 or L2 loss. So let's say this pink line is our optimal model parameters, and so we'll call that GW star x. Now, our aleatoric uncertainty is this here, because we can't get a better model which will reduce the distance between these points on the line, because we're limited in the model that we're using. Whereas our epistemic uncertainty would be moving from this yellow line to this pink line, because we can reduce that by just changing the y-intercept and the gradient of the line. Those are two model parameters that are in our control. Does that hopefully make sense? Yeah. So hopefully I answered your question, Victor, as well. Awesome. Cool. I think if there's no other questions, we'll end it there. If there are any other questions at any point, just drop them in the AI channel or on the comments of the video. I'll try and get it uploaded soon. But yeah, thanks for coming. Let me stop the recording.